Hello, today we're going to be working with the hexaphenylbenzene. This corresponds to the chapter 41 of your book. This is the final reaction to make hexaphenylbenzene, and it involves two different pericyclic reactions. Pericyclic reactions include cycloaddition, electrocyclic ring opening or ring closing, sigmatropic rearrangement, and chelotropic extrusion. R.B. Woodward and Ronald Hoffman received the 1965 Nobel Prize in Chemistry for working out the rules to predict and understand pericyclic reactions. The rules are now referred to as the Woodward and Hoffman rules. These are taught in advanced organic chemistry courses here at UTEP. Here are some examples of pericyclic reactions. The cycloaddition. One of the examples is a reaction that you saw in your courses named the Diels-Alder reaction. The pink arrow shows the electron pair movement. There is the electrocyclic ring opening and also ring closing. The green arrows show the rotation around the bonds. The sigmatropic shifts. One example is the Cope rearrangement that is shown here. And lastly, the chelotropic extrusion, which is something that we're going to be seeing in your current session. The hexaphenylbenzene synthesis combines two pericyclic reactions. First, a Diels-Alder cycloaddition that comes from diphenylacetylene triple bond and our previously synthesized compound, the cyclopentadienone. This will form the corresponding six-member ring with a carbonyl compound sticking out into the 3D dimension. After that, the chelotropic extrusion is going to eject the CO out of the molecule, making the hexaphenylbenzene. This is a molecular orbital theory calculation of the Diels-Alder cycloaddition reaction. Here we can see how the diphenylacetylene approaches the molecule and forms the new bonds, making this new six-member ring and having the CO group sticking out towards us. This is the calculated reaction coordinate for the cycloaddition reaction. You can notice that the activation energy is 46.3 kilocalories per mole, and the reaction is exothermic of minus 13.1 kilocalories over mole. The high activation energy means this reaction must be heated quite a bit to initiate. The exothermicity means the reaction is favored downhill and will generate heat. Here we have the molecular orbital theory calculation of the chelotropic extrusion. We can notice that the CO is getting ejected out of the molecule and the new configuration makes the hexaphenylbenzene. Note that the bonds to the carbon of the CO bond are so weak since the molecule is highly strained that they don't appear at all in the calculation. This is the calculated reaction coordinate for the chelotropic extrusion. There is almost no activation energy, 1.4 kilocalories per mole, because the molecule is so strained. The low activation energy means this reaction would occur spontaneously at room temperature. This is a very exothermic reaction of about minus 46.7 kilocalories over mole. Here we explain the experimental procedure. We're going to mix 0.5 grams of tetraphenylcyclopentadienone and 0.5 grams of diphenylacetylene. We're going to heat strongly using the heating manuals for 15 minutes while stirring with a glass rod or a spatula. After this, we're going to add 10 ml of diphenyl ether and stirring while it warms until solution looks homogeneous. We're going to cool the solution to room temperature. Add 20 ml of mixed hexanes. Cool the solution in an ice bath and collect the product via vacuum filtration. There are some practical considerations. Because of the high activation energy for the first step, this reaction requires much heating. Use caution because your glassware will be quite hot. Clamp your flask and place a ring clamp under your heating well so that it can be lowered when you need to cool the reaction. Clamping your flask will protect against burning your hand. The procedure calls for use of a glass stirring rod, but a spatula can be used if the glass rod is not available. Be careful to not poke a hole through the flask. The diphenyl ether will keep bringing the reaction to completion by keeping everything in solution. We're going to be using diphenyl ether as a solvent. This compound is usually a solid at room temperature. Usually the source bottle must be gently heated to melt the solid in order to measure out the solvent for the reaction. Your TA will do this for you. Hazards. This reaction needs to be heated and there is more than one fire danger. When one adds the diphenyl ether, use care, as this can inflame if the flask is too hot. Remove the flask from the heating well before adding the diphenyl ether. Be especially careful about adding hexanes. Make sure the reaction has been cooled to room temperature. When cooling your flask in ice, let it cool first before placing it in ice. Pyrex glass can withstand a large thermal shock, up to a delta of 160 degrees, but it can sometimes break if the thermal change is too fast. Remember that we're going to be doing IR and NMR spectroscopy by the end of your session, as well as UV spectrum in chloroform.